Yeah, all right. So are you ready? Or?
Sure.
Yeah, okay. Yeah, so I think we'll just start them and then people will join in later on. Yes. Okay, so it's my pleasure to welcome Nat Trask from Sandia, who will be talking about convergent and structure preserving architecture for scientific machine learning. Yeah, thank you.
Okay. Thank you, Boumediene, for the invitation. And this is a great seminar, and especially during COVID, it's nice to be able to reach out to people virtually. So what I'm going to talk about today is some of the work that we've been doing at Sandia with data-driven modeling at the labs. We have a lot of high throughput data. There's a lot of experimental facilities that we want to take advantage of and so on. So to start off, what I'm going to do is contrast scientific machine learning to more traditional machine learning. So for all the kind of things that people usually do in the machine learning world, like classification, image processing, NLP, and so on, there are these sort of custom machine learning tools or architectures that have emerged and are kind of the secret to getting all this stuff to work, right? Like convnets for image processing, RNNs, ResNets, LSTM for time sequence data, and so on. But broadly, a lot of these kind of, in this kind of world where you're trying to do classification, in general, having very high accuracy is kind of an issue because it leads to overfitting and so on, right? And so oftentimes people are very happy with a relatively low accuracy because it tends to generalize better. So in the scientific machine learning world, things are a little bit different. There are different requirements. So for example, we're very interested in complex geometries, typically CAD geometries, things that are actually going to be built and used in engineering settings. So we don't have these kind of, Cartesian grids of pixels. We have this very complex geometries. In contrast to traditional machine learning, our data is typically much smaller, right? So we're not Google or Facebook. We don't have billions of profiles that we're going to mine through in order to get our data. We have these experimental facilities, and I'll talk about some of them, where we might be able to do 10 or 20 experiments maybe. And so for those experiments, there is a lot of data. Each one of these experiments might consist of just a massive amount of information streaming out of it, but we can only afford to do a single realization. And so for these kind of traditional numerical simulation tasks, right, we want to do things like learn constitutive models, we want PDE-based physics models or dynamical systems, and so on. And we want to do things like inverse problems and uncertainty quantification for these engineered systems. And typically we have our own set of tools that are important, right? So we have things like finite element spaces or kind of classical approximation theory. We have things like variational principles that go along with finite element methods. And we also have more subtle geometric and algebraic structure that's typically very important to preserve in the forward simulation world, right? So we have these unique requirements, small data, we need accuracy, we need stability. And so what we'd like to do is develop some sort of hybrid version of traditional machine learning with these more, as a way to assimilate these kind of engineering requirements. So in the scientific machine learning world, over the last few years, right, maybe 4 or 5 years ago, everyone was taking their big simulations and plugging them into TensorFlow and seeing, if you could accelerate things or so on. But typically, unless you have a ton of data, engineering forward simulation models in those settings tend to not be stable, right? So you might be able to fit your data well, but then when you try and extrapolate and so on, your models will kind of blow up, right? And then in the last 3 or 4 years, these ideas have been around for a couple decades, but in the last 3 or 4 years, physics-informed machine learning has emerged. And the idea here is that you take your data, right, which you're trying to fit a neural network to, but you add some sort of regularization, right? So you assume some sort of PDE structure. For example, if you're looking at a flow, you might assume that your velocity field satisfies the Navier-Stokes equations, for example. And you have these kind of penalty terms. And what that will generally do is it alleviates these kind of data requirements. You'll get models that generalize better and so on. but you have to calibrate these penalty terms. And in general, these physics can only be enforced to within optimization error. So what we've been developing is what we're calling structure preserving machine learning. The idea is that you design a neural network architecture exactly so you get whatever these properties are that you want out. And so what we'd like is that these surrogates have the same sort of accuracy, stability, physical realizability guarantees, things like conservation or involution structure for electromagnetism. And that these properties hold even if you have a single data point, right? So you're not relying on things like universal approximation theorems or so on in order to extract a good data-driven model. Another place that we're using these things in the labs is to develop high-dimensional surrogates. So in uncertainty quantification and optimal design, it's very frequent that you'll have a model that's parametrized. Right, so you can think about this abstract problem, right, where you have some solution u sub theta, right, and you'd like to calibrate your model to best match some sort of experimental data or so on. And as a concrete example, you could think about something where you have some sort of material property, right, that you're trying to calibrate. And this could be all sorts of things, right? This could be porosity and subsurface flow, material properties, chemistry, coefficients, all sorts of stuff. And so typically these systems that we'll be considering are, you have your spatial dimensions like maybe 2D or 3D, but then just an absolutely massive parameter space. And so some of the architectures that I'm going to discuss today actually break the curse of dimensionality. And so they provide a great platform for doing this kind of modeling. So what I'm going to do today is talk about, I'm going to start by mentioning a couple motivating examples that my group's been working on. And that these problems have these sort of unique requirements in terms of accuracy and structure preservation and stability. So I'll break the talk up to talk about those two things separately. And what I mean by accuracy is, in the finite element or the forward simulation world, what people would do is you'll typically use some sort of finite element method or some sort of means of solving a PDE in order to predict a system. And so for high consequence decision making, the kind of things that the National Lab tends to care about, you want to see that if you do some sort of grid refinement as you refine your mesh, you'll converge to a well understood solution. And so what we'd like is the sort of analog for a neural network as you go to something wider or deeper, right? It should also converge in a certain sense, right? And then the second question, structure preservation stability, right? We have these models that we'd like to incorporate into sort of an ecosystem of other codes, right? So for example, at Sandia, we maintain a E3SM, which is the Earth systems model. It's like the climate model for the planet. It has all sorts of components for the atmosphere, the ocean, land ice, sea ice, and so on. Right? Each one of those models has a whole bunch of other models. And so if you have a data-driven machine learned component, you have to be able to hook it into this ecosystem without breaking everything else, right? So you need to provide these sort of guarantees about stability, that it's not going to lead to physically realizable solutions and so on, right? And so these kind of requirements give, this leads to these sort of practical environments. So any of these kind of extreme or high risk scenarios, you have to address these two kind of phenomena. Okay, so the first example that I'll mention is development of, is working on semiconductor design. And so typically, you'll have a semiconductor like a transistor or something. And these devices are governed by the drift diffusion equations. So these drift diffusion equations, you can simulate with finite elements. And you can basically, you could get most of the physics that are going on with one of these PDE models, but they're quite expensive. So you might have like millions of elements, for example, for a single semiconductor. And of course, an actual system scale electrical circuit design might have millions, billions, who knows how many of these things, right? So it doesn't scale up and you have this multi-scale problem. And so what people do is they develop what are called compact models. But the idea is that it's an equivalent circuit that, you know, using the kind of things you would learn in introductory physics, like Kirchhoff's laws and so on. You cook up some circuit that has the same response as this PDE model. And now these circuit models are developed empirically. So it can take for many components up to a decade in order to develop one of these. It's very empirical. People kind of like squint at experimental data. These PDE models, they say, what if we added another loop here, a capacitor there, a diode there, and so on. But they do get these efficient circuits, which they can scale up. So the issue is these things are, you know, one, what happens if you have a new material that you want to try out, right? You can't go and take another decade to develop a whole new model. And then for a lot of the electronics that we develop, they go up into space on satellites, and there's solar radiation, for example. So they're getting blasted with radiation from the sun, and that actually changes the physical response of that circuit. And now you need a whole new model, right? And obviously you can't just take a satellite and land it and take a decade to put together a new model, right? So you need something that's automated and kind of turnkey. So one workflow that I'll talk more about later is we take these kind of high fidelity models, we do some topological data analysis or partitioning in order to break this device up into physically relevant subregions. And once you have these subregions, that induces this connectivity graph, right? Where you have a node for each region and an edge for connected regions. And so this provides a what we call a model backbone. And now what you'd like to do is dress up this model backbone, right? You'd like to attach a model to this graph, so you get something that can be simulated with a production circuit simulator. So so SPICE or ZEISS is a pretty common one that electrical engineers use a lot. And the idea with this stuff is that you'd like this entire process to run in an hour, maybe, as opposed to decades. A second example that I'll motivate some of our work with is the Z machine at Sandia. So this is a pulse power fusion device, and it's not a power generator, right? It's not meant to generate fusion power that you can use to like power homes. It's a experimental facility for generating over a short window of time a fusion energy environment so that you can do foundational scientific research. And what this is a big building. It's huge. It's basically like the size of an ice hockey rink. And around the perimeter of the building, you have like 1 or 2 story tall capacitor banks, right? And the way this thing works is it's no different from like a disposable camera that you'd wind up and then you'd hit a button and then it discharges as a flash. What this does is it powers up all of these huge capacitors, and then it dumps all of that electricity, you know, generates electromagnetic fields in a target region at the center of this device, right? And what that does is for a very short amount of time, it generates a fusion environment, which can be used for all sorts of kind of foundational science. And this is a user facility that Sandia supports. So one type of experiment that people often do is they use these electromagnetic fields to launch a plate, a flyer plate, into a material under test. Right? And you could think of this just as a ballistic experiment. People also do this with things like rail guns or pneumatic guns or so on. And so once you launch this plate into this test material, you get to observe how a shock propagates through that material. And so the objective is that you get to observe one of these Riemann problems. And then what you'd like to do is fit an equation of state to that data, for example, right? So if you do this experiment, if you extract an equation of state, then you can break that off and you can pass it to a CFD code, for example, and then people can design things and using these kind of equations of state. And so, you know, these have at least as many complications as standard CFD code if you want to do this kind of data-driven machine learning of an equation of state. Like it has to be compatible. It has to be thermodynamically compatible and so on. So there's a reference down here to a paper where to that work. So like I mentioned, accuracy and stability are a big challenge for these kind of models. And so when, at least when I got started with machine learning in this kind of, PDE based context, the first thing I did was I tried to just regress sine 2 pi x on the unit interval. That's what I do with finite elements and any kind of discretization for PDEs, just so you get a sense of how it converges, what are, just to get your hands on it. And I was kind of shocked and appalled because it doesn't matter how wide or how deep you get, you immediately saturate. You very quickly saturate around 1% error, 0.1% error. This is a slight oversimplification, but you always hit this kind of barrier here. And due to what people call optimization error, or you're getting stuck in a local minimizer or so on. And so what this first part of the talk, what we'd like to be able to do is break through this barrier. So that way we know that you can be confident in your answer, right? Like if you get a prediction and you double the size of your network, that it gives you the same answer, right? Then you can be confident that that you're actually resolved. And so this first part is how are we gonna build networks with those kind of desired convergence properties. And this came out of a reading group at Sandia, and basically we dug into the approximation theory literature, and we wanted to understand how, regardless of what you can realize during training, what is the optimal convergence that you could hope for if you were somehow able to realize the global minimizer. So that way we knew how much time to spend developing new optimizers and so on, right? And if you haven't seen this kind of thing before, this is just some intuition for how a multilayer perceptron actually works, right? So if you take all of the hidden layers and you identify their weights and biases with these hyperparameters chi h, h for hidden, and then typically these are capped off with a linear layer, right? Whose weights you can identify with chi l. Then the output of a neural network is going to be a linear combination, right, from the linear layer, a linear combination of the outputs of all these hidden layers. And from a numerical analysis perspective, you can view this as the hidden layers defining some sort of data-driven basis, which is calibrated to best fit your data. And then these output layers give an optimal representation of your data in terms of that basis. So there's lots of work in the literature establishing convergence results, convergence with respect to width, with depth, and so on. But at the end of the day, right, this is regressing sine x, sine y, right? What you can see, and these are planes associated with ReLU activation functions. And so what you can see is over the course of training, a neural network is basically adapting this basis to your data. So over the last year, we have this kind of sequence of 3 papers. The first, developing fast optimizers once you take that adaptive basis perspective, then applying that to looking at classification problems, and then finally culminating in this partition-of-unity networks paper that I'm going to talk about today. But the punchline here is that, like I mentioned, you have this barrier. And now we're going to introduce a special optimizer and architecture, which lets you realize this kind of algebraic HP convergence. So if you're interested in details, I'd recommend you to check out these papers if you want to see kind of what the progression of what led to this. And so I mentioned that we were digging into the approximation theory literature. And this one paper in particular, I very highly recommend, really gets at the nuts and bolts of what's going on. And so in this paper, they established that deep neural networks can emulate a super broad class of approximations, nullifying elements, free knot splines, global spectral approximation, RBFs, and so on. And so basically what we did is we zoomed in on the part about HP finite elements. And it turns out that there exists a neural network. You may not be able realize it during training, but there exists a way of choosing weights and biases so that a neural network can both partition up space, and then there's, with even more depth, on each one of those partitions, it can emulate monomials. So once you have monomials and a way to localize them in space, that's basically a path to HP convergence. There's obviously a lot of details there. I definitely recommend checking out that paper. So if you're not familiar with a partition of unity, it's very simple. It's just a collection of functions, each of which are positive and sum to 1, right? And in a canonical example are if you have a domain in space and you build a mesh, a partition of disjoint cells whose intersection are 0. And if you choose the set of indicator functions on each one of those cells, that would form a partition of unity, right? And so if on each one of these partitions of unity, we attach a polynomial space, this would be a way of representing a DG, a discontinuous polynomial space, like what people use in a discontinuous Galerkin method, for example. And the key thing, again, is that this allows you to localize approximation. You can use polynomials to approximate a truncated Taylor series on each one of these domains. But the idea with this is that, so we're used to working with partitions of unity that look like that, but there's nothing that says that they can't look more complicated, right? So these partitions could, in principle, be diffuse. They could kind of bleed into each other and so on. And so the idea behind the architecture that we've put together is that you have these two pieces. The first is a partition of unity. And what this is a means of parametrizing a partition of unity, like I mentioned. And so we borrowed this from the classification literature, right? If you have any hidden layer here, it can look like anything at all. We looked in this paper at multilayer perceptrons and RBF nets. You could do autoencoders, you could do convolutional networks, whatever you'd like. And then you feed that into a softmax, right? This is traditionally a way of parametrizing a probability density distribution. But for us, that's also something that's positive and sums to 1, right? So that can be interpreted as a partition of unity. And now the output of each one of these neurons coming out of the softmax, for each one of those, we'll attach a function space. So to keep it simple, you could think of this as a polynomial space, but this could be any general Banach space here. It could be singular functions, it could be Gaussian processes, or so on. And so you have this P, which is a vector for this function space, a basis for the function space. And then you have a vector of coefficients expressing on this partition an optimal representation in terms of that basis. And so the thing that's really nice about this is that if you freeze the hidden layer parameters and you're solving a convex loss, or specifically we're looking at a root mean square loss, then you get a least squares problem for these polynomial coefficients, right? So basically what that says is if you fix your current partition, you can get the globally optimal representation of your data just by solving a linear system, right? Then at the next step of training, we'll do a step of gradient descent. This perturbs your mesh, if you want to call it that. And then you alternate back and forth and back and forth. Okay, so here's a little movie, just giving you a sense of how it works. We want to regress this red dashed line. It's piecewise quadratic. Blue is our current representation of it. On the left, I'm plotting, this is just in 1D, we're plotting each one of the partitions. And so the hidden layers are randomly initialized to start, so there's nothing really special to see here, right? They just kind of break up the domain. And so over the course of training, doing this alternating least squares gradient descent, you see the partitions evolve, and then there's all of a sudden a phase change, right? And it snaps into these indicator functions, right? Basically what's happening is if you or I or anyone with a background in a scientific computation wanted to approximate this function, they would know that you would need to build up a piecewise, you would need elements which conform to these discontinuities at the ridges here. And typically what we have to do is go into meshing software and put this together, right? This is able to discover these partitions all on its own without any need to do that. And in a certain sense, multilayer perceptrons are capable of doing the same kind of thing. But the problem is that everything is mashed together all at once. So breaking it together, you can use this partitioning scheme to do what neural networks do best, right? Partition space. Usually they're used to partition, this is cats, this is dogs, and so on, right? And then we're going to use these kind of mature, polynomial regression is about as old as it gets to do the approximation. So that way the neural network doesn't have to both partition space and approximate simultaneously. We have an error estimate for this, which basically says if you are able to get partition functions which are compactly supported, and this is what I mean by aspirational here, because we don't have guarantees that will be realized during gradient descent. But if you are able to get them to be compactly supported, then this, you get a completely standard Taylor series argument that pops up, right? And that gives you, if you're working with mth order polynomials, you get the support of those partitions to the m+1. And this whole thing is independent of the ambient dimension, right? So if you can get partitions which break up space and take advantage of some latent low dimensional structure, right? Like if your data is sampled from a manifold, then you're able to get m+1 convergence independent of the dimension. So there's some details about how to actually train this. So to encourage it so that you do get compactly supported partitions. The details for that are all in this paper. Just basically some regularizers and things like that, right? And so this is the picture that I showed before. The details are, I'm looking at data sampled from the X and the Y axis. So this is like a latent low dimensional manifold. You get a bunch of points on this line, a bunch of points on this line. So there's a latent low dimensional manifold here. And for the hidden layer space, we're working with an RBF net, which basically gives you a bunch of normalized Gaussians with trainable centers and shape parameters, right? These are the hyperparameters that are being learned. And that's enough for smooth data to realize this kind of HP convergence. So the result I showed before where you had discontinuities in the data, that's where ResNet's better because you can use piecewise smooth activation functions, which are able to conform to boundaries. We found that this kind of architecture works best for smooth data. So I talked about high dimensional approximation, and here are just some kind of pedagogical examples for showing how that would work. So the idea here is that we're going to use an autoencoder to find a set of local coordinates x hat. And then once you have these local coordinates, then we're going to feed that into a partition of unity network. And so as an example, right, you can imagine data sampled from a circle in R2. In polar coordinates, right, you have theta, right? So there exists a single dimensional coordinate, right? This is what we would hope the autoencoder would pick up. And then what we're hoping is that the partition of unity net will find a partition of this latent low dimensional manifold and then attach a local polynomial basis to this. That's right, I've been having trouble with this video. Basically what you see, for whatever reason, this video is freezing, no problem though. So this is a sketch of the circle. And what I'm plotting here in the ambient space, in the 2D space, is the output of the softmax, right? And these level sets say whether you're in partition 1, partition 2, partition 3, partition 4, and so on. And you can see that this is after the first step of training. You can see that it's fitting locally within these ambient coordinates, right? This is this theta direction that it's discovered. It's fitting a locally linear space here. We're trying to approximate this this tanh function. And over time, what it'll do is it'll it'll adapt both the local coordinates and the partition simultaneously. And if this video is working, it would be converging down to like 10 to the minus 4, 10 to the minus 5. Okay, so just to make it super explicit that this does break the curse of dimensionality. Now, if you take a d-dimensional hypercube and you grab a line, a 1D manifold that goes from one corner to catty corner to the opposite corner, and along that line, you define this smooth function. You can look at whether d is equal to 1, 10, 100, 1,000. This approach gives you a very accurate representation of the underlying function, independent of the number of dimensions that you're in. And so this is why we're thinking about using these things in UQ and inverse problems and so on. So that's the first part that I wanted to mention. Now the second part, I'm going to focus on this kind of second architecture, which is aiming at physics compatibility, stability, and well-posedness. And the idea for this is, for those from an engineering department, this is kind of in undergraduate engineering, people don't tend to start working with PDEs until they're at the graduate level, or at least the upper undergraduate level. And the first way people are taught to analyze systems is in terms of control volumes, right? So the idea about differential models is that they're really good for calculation. That's why people use them in the 1800, Fourier and et al. Use them because there were no computers back then, right? And they let you do functional analysis. They let you derive a lot of things. And so there's historical reasons that people work with differential models, PDEs, and the like. But it's arguable that integral analysis is kind of a more fundamental means of describing a system, right? So if you look at a volume of a domain, you can make the same kind of conservation law arguments, right? That the sum of the fluxes is the rate of change of whatever a conserved quantity is on the inside of this control volume. But this is purely a geometric thing, right? You're talking about the differential geometry and how things are evolving through these surfaces. And so the idea that we're going to pursue here is to use a graph to represent this integral analysis. That a control volume can be identified with a node, and the fluxes around the boundary of the control volume can be identified with edges and so on. And this is actually, this has ties to the early roots of finite elements and algebraic geometry. So in the early 1900s, this is how people, again, computers had limited computational power. And so people would do like spring damper systems. They have all sorts of electrical circuit analogy models in the engineering world. So we're kind of going back to that and taking the mathematical tools from that. And so in a more contemporary level, numerical analysis in the last decade or so, there's been a big push to recast the analysis of numerical PDE schemes in terms of differential geometry in algebraic topology. And so so-called compatible spatial discretizations are basically methods which look to the Stokes theorems, the Gauss divergence theorem and Green's theorem and so on, as a means of approximating your div, grad, and curl. And by tying things to these more fundamental theorems, that allows you to preserve topological structure in your governing equations. And by doing that, basically you mimic properties of the continuum operators, right? So if your continuum equations are conservative, your discretization will be conservative. If you have a maximum principle, maybe things related to the eigenspectra, all sorts of things along those lines. And so, there's not enough time to really get into the guts of how these things work, but I'd just like to give a flavor of it. And so for these schemes, there's generally two ingredients. The first would be a topological structure, and that would be something like a mesh that people always use to solve PDEs. Right, so that would be cells, faces, edges, nodes, and a boundary operator connecting cells to faces, faces to edges, and so on. And so what we're going to do is we're going to use a graph as a surrogate for this kind of topological structure. But the second ingredient is symmetric information. So typically that would be something like cell volumes, face areas, edge lengths, and so on. And graphs have no notion of that. Graphs are purely topological. And so we're missing the second ingredient. We're missing this metric piece. And so the idea is we're going to machine learn this missing metric information from data. Just to make this concrete, if any of you have ever worked with a finite volume scheme, right, you'll have something which is a sum over, given a cell C, you're going to sum over the faces F that surround that cell, and you're just going to add up all of the fluxes surrounding that. So this is what I mean by a topological structure, right? It's just about connectivity. You grab all those things, you just add up all those numbers, right? The metric information in this this is like the lowest order version of it, so it's pretty simple. Here, the metric information would be the cell volumes, which you have to divide the fluxes by in order to get something that converges to the vector calculus divergence that we all kind of know and love. Now I'm just going to blow through this, right? But these are the way these things work. You have what's called a chain complex. This would be the cells, faces, edges, nodes. For a graph, these will be k-cliques, right? So an oriented k-tuple of nodes. And so edge and a node, you could think of nodes as the boundary of an edge. Those would be examples of a one clique and a zero clique, and generalizes upward for high order tuples. Now, to each one of these things, you attach a number, right? Think about how for a face on a cell, you might consider fluxes through that face, right? So we're going to associate a number to each one of these objects up here, and we'll call that a cochain. The number is a cochain. The cochain complex is how all of these things are connected to each other. And they're connected together through the generalized Stokes theorem, right? So once you have a chain, right, think of like a cell and the faces and the boundary of the cell, right? That induces an exterior derivative, right? Think about how the Gauss divergence theorem defines a divergence operator, right? And that co-boundary operator or discrete exterior derivative links all of these things together. And now the final piece is you have these exterior derivatives or co-boundary operators. You define an inner product in such a way that it induces what's called a co-differential, right? And so all this sounds kind of complicated, but it's really simple, right? So the Gauss divergence operator defines, you can think about a discrete divergence operator here. If you choose an L2 inner product, right? This basically just says integrate by parts. And what will pop out is a gradient operator, right? And so the point of all of this is that it kind of propagates structure down, which is that the boundary operator is an exact operator, which is that the boundary of a boundary is always equal to 0. That's like a topological property. And each one of these derivatives will inherit that property, right? So in terms of plain language, right, this preserves vector identities like the divergence of the curl is equal to 0, the curl of the gradient is equal to 0. And that actually has some pretty deep consequences later on. Okay, so once you do this whole thing, right, so for this big commuting diagram, along the center here, this big center rung, you have the standard graph calculus, right? So this is a graph gradient, graph curl, graph divergence, and so on. And their adjoint operators. And what we'd like to do is kind of upgrade that graph calculus, right? A graph gradient doesn't converge to a vector calculus gradient in any useful way, in the useful way that we would need it in order to build a physical model. So the idea is we go back to those inner products and we parameterize them. So we introduce diagonal tensors with positive trainable coefficients on the diagonal, right? And so basically what that does is that lets us upgrade these graph calculus operators And now we have these data-driven co-boundary operators and co-differentials, right? And so in the same way that, you get a graph Laplacian by taking the composition of a graph divergence and a graph gradient. Now we have a graph, a data-driven Laplacian that comes from upgrading this. And so I kind of alluded to the fact that the graph calculus has this exact sequence property, right? Like a graph curl of a graph gradients equal to 0, right? That would correspond to going from here to here and from here to here. By virtue of this commuting diagram, right, you can see that that gives you the exact same thing. And so we're preserving all of that structure, right? So we've fleshed out this kind of topological structure in a way that now we can incorporate data without losing any of this, this desirable structure. So if you haven't seen this stuff before, this probably seems, it's very mathy and its utility might not be clear, right? But the reason we're doing this is very, very practical. So it gives you a lot of concrete things. It gives you graph, div, grad, and curl, which are locally and globally conservative, right? So this will give you a way of preserving conservation laws at a discrete level, independent of the amount of data that you have. I briefly mentioned, right, that you get a Laplacian, which is the composition of a divergence and a gradient, right? And they're higher order versions of Laplacians. So this will admit trainable Laplacians, and they're guaranteed to be symmetric, positive, definite, and invertible. And also all the kind of things like Poincare inequalities and so on that you need to analyze them. So this opens the door to a lot of rigorous analysis. And I mentioned this exact sequence property, right? Div curl 0, curl grad 0. This is probably the most important piece, especially for things like electromagnetism. So that gives you access to a Hodge decomposition. You might have seen this in undergraduate physics, right? Any vector field can be written as like the curl of a potential plus the gradient of a scalar potential. This is kind of the more abstract version of that. And that's absolutely critical for handling Maxwell's equations correctly. There's a constraint that the magnetic field is exactly divergence free. People call that an involution condition. And this lets you preserve this structure at a discrete level. And I'll just mention, we have theorems for all this kind of stuff. If you're interested, you can check out this paper. But for the remainder, I just want to show how you can use this stuff, right? Because it's a little bit in the abstract, but it gives you something really concrete, right? So imagine you have the Darcy equations here. You'd like a surrogate for that. You have a high fidelity PDE solution, right? So you have a very fine mesh on this side. And so what you're going to do is you're going to partition this mesh. And once you've partitioned this mesh, that gives you this graph backbone that you'd like to hang a model on top of. And your training data is that for each node of this mesh, you'd like it to reproduce the moments of your high fidelity simulation, right? So you'd like something that is, you'd like something that's cheap and low dimensional, but it inherits the accuracy of your high fidelity model. And in a certain sense, this is like a reduced order model, but the workflow is totally, this is based on a control volume analysis rather than the usual do PCA, do a least squares residual minimization and so on that people do in Rhams. So there's a lot of consequences of that. But anyway, so once you have this, right, that's the data that you'd like to reproduce on this graph. The way you define your model that you'd like to train is you reach for the analogous graph operator, right? So here conservation is encoded by this thing that says that the sum of the divergence of the fluxes is equal to the sources, right? So here we have this data-driven divergence of the fluxes is equal to the sources. And then the fluxes, and again, this is physics, right? This is what encodes the conservation structure, and you really can't mess with this in a certain sense, right? But down here you have the fluxes, right, which are typically more empirical. They come from homogenization, or sometimes people just kind of cook them up and try and calibrate them after the fact. So the idea is that in a traditional Darcy problem, you'd have gradient fluxes. So we reach for the graph gradient operator, this data-driven gradient operator. And you can see this term here is where that metric information pops in, right? This is a trainable thing. In a certain sense, this is like fitting a resistor model, like a resistor network to your data. But then you have a black box neural network here, right? And so basically what you're left with is a general, this is a universal approximator. You can approximate any sort of nonlinear flux, but you're setting it up as a perturbation of a nice elliptic operator. So this holds wherever, you can do this anywhere on that commuting diagram on the so-called de Rham complex, right? But at the end of the day, you can show that the model that pops out has this very nice structure. You have a nice invertible bilinear form. This is always some sort of Hodge-Laplacian. And this is where all of the metric information comes in, here and here, right? And so these are trainable parameters. And then you have this nonlinear perturbation. This is where all of your neural network parameters live. And so if you can fit your data to a model of this form, using an equality constraint, right? Then you're guaranteeing that it doesn't matter what your data says, the resulting model will inherit all of this pretty sophisticated structure, right? So the natural question is, can you impose that equality constraint? And it turns out it's actually very simple to set it up. This, or to analyze, the elliptic bilinear form has a Poincare constant. If you assume your nonlinearity is Lipschitz, right, it has a Lipschitz constant. And basically what you want to show is that this nonlinearity is sufficiently small relative to the diffusion. This is no different from, this is kind of an old trick in numerical analysis. All the time, people add artificial viscosity in order to stabilize a method, right? And it's the same kind of idea here. And so you can find these kind of results in any graduate textbook on nonlinear elliptic PDE. So it makes sense to try and do an equality constraint optimizer for this. It turns out that you can do PDE constraint optimization, PDE in quotes, because this is a graph model. There is no actual PDE here. But you can solve a forward problem, right? So basically, given your current guess for the model, you can solve it, right? That gives you estimates for the flux and the state variable here. Then if you go to the KKT conditions, right? The gradient of this whole big thing with respect to u has to be equal to 0. That gives you an equation for the adjoints. The adjoint problem, which basically tells you what these Lagrange multipliers are. And now once you know these two things, you can take a step of gradient descent to update your model, right? That updates the metric information and the neural network weights and biases, right? And then you can just iterate on that. I've got a lot of pictures here kind of showing how this works out. This is Darcy equations with a point source and a point sink, right? So basically you get flow that goes throughout this whole domain, but you have some sort of inclusion. So there's a jump in the material properties that's like a factor of 100, right? So this makes it difficult for flow to go through. And we have some comparisons showing, basically that even if you have a very, very coarse representation of space, this will train and reproduce high fidelity moments. Basically, it turns out to machine precision, right? So this model form is sufficient to actually capture exactly what's going on, and we can realize that during training. I'm a little tight for time. I'm not gonna go through the details of these. This is a similar problem, point source, point sink at the bottom left and top right corner. You have some inclusion where the material properties, you have kappa 2 is the material coefficient, kappa 1 in the bulk is equal to 1. And we're going to say that this material coefficient is proportional to the pressure drop, the delta phi from one corner to the other one, right? So basically what this says is as you force the system more, it gets more diffusive. And you can see it, this is like a pretty coarse graph, but it's able to reproduce well the actual high fidelity solution, which is the dashed line. The same thing works for electromagnetism. And the thing to, so down here, this is a similar thing. The diffusion coefficient, in this case permittivity, is proportional to the jump in the magnetic field, or sorry, is proportional to the magnetic field being imposed. And so the thing to notice for this stuff, right? This plot in the bottom left, I'm looking at the profile of the magnetic field that gets fit across this line. If you, and this holds in the forward simulation world, if you're simulating electromagnetism with regular finite elements, if you're not very careful, you'll get these kind of ringing phenomena. And it's kind of a technical explanation about what goes into that, but there's like decades of research in this in the finite element world, which goes in how to properly simulate Maxwell's equations. Just in a complete hand wavy way, I'm just going to note that we're getting the same kind of, we're getting a sharp representation of this jump in the solution. So the important highlights is that this surrogate is exactly divergence free in an integral sense for the magnetic field. You get these sharp interfaces I mentioned. It conserves circulation, and it's guaranteed to be solvable, right? So the point is that you can take this surrogate and now you can embed it in a larger scale production code, right? So for things, we do all sorts of stuff with magnetohydro dynamics. This can be a nice component model that you hook into your kind of ecosystem of other things, right? And again, I mentioned this example at the beginning, right? That we have these kind of high fidelity drift diffusion models. This is the process that we're using to construct a surrogate for these kind of components that you can turn around and you can now scale up to in a kind of a means of handling the multi-scale challenges for system scale circuit design. So I will, maybe I'll wrap up here and take some questions. I want to mention my collaborators, especially Xiaojia Hu, who has done a ton of work with us on this data-driven exterior calculus stuff. And I'd just like to mention that we have a ton of projects, both related to these kind of applied math, algorithmic, theoretical things, but then also applications problems. And we're trying to recruit both new postdocs and also looking for academic collaborators at other national labs and so on. So if that's something that's of interest to you, please feel free to send me an email. A lot of, there's tons of details that I didn't really have time to get into. I just wanted to highlight a couple things. This paper right here is the partition-of-unity network stuff. This is the data-driven exterior calculus on graphs stuff that I mentioned. This paper here shows us applying this to semiconductor development. What else should I mention? This one here is the stuff about extracting equations of state from data and so on. So again, if you have any questions about any of these things, please feel free to send me an email. I'm starved for social interaction in COVID, so I'm always happy to Zoom or anything like that if you want to get into the details. And also, I didn't have time to get into this other work that our group's doing. We also have some codes that we're supporting. One basically for doing scientific machine learning on unstructured data. Think convolutional networks, but you're not stuck on a Cartesian grid. I actually have a talk about this on YouTube if you search for GMLS-nets, if that's something you're interested in. Also, this other framework for extracting physics models from data. So I made my little pitch, but I'll stop there and hopefully take some questions if there are any.
All right, thank you very much. Thank you. Any questions?
Yeah, I liked very much the way you can enforce physics at every iteration. And I wonder if there is an example or using this in weather prediction and climate models.
Yeah, that's especially important for climate, right? Because climate in general, they're always in the Ford simulation world, they're running on the bleeding edge of what they can actually afford to simulate, right? So everything's always under resolved. You're never actually resolving all the turbulent processes, and then in particular, we're really interested in using this for cloud models, which is something that's difficult to model in general, and it's kind of prime for data-driven modeling. What I've presented today is the elliptic PDE version of that, right? All of this stuff is basically tailored toward second-order elliptic problems and, or at least, diffusion-dominated problems. Right now, we are wrapping up a project on handling singularly perturbed advection diffusion. As usual, you have to be really careful with how you handle advection and upwinding if you actually want, for example, something bounds preserving, right? Like you don't want density that's going to drop below zero for the shallow water equations in climate, for example. So that what you're describing is definitely something we have our eye on for the future, but right now we're working on these more fundamental things, and maybe in a year or so we'll have to talk about that.
Okay, because in those models they tend everything they don't know, they parameterize, and your approach could be a very good test for these parameterizations.
Yeah, it's just so difficult, right? So we tend to be on the careful side in my group. For sure, you could just take this stuff and plug it in, and probably it would work well. My concern is, especially like these giant E3SM, for example, the climate code. It's such an effort to get something in there. So I'm personally adverse to trying things out until I'm positive they're going to work. But yeah, I agree. I mean, it's definitely something that is worth trying.
Okay, thanks. The codes you mentioned are available?
Yeah, so we actually have code for all of this stuff that we can share. These two down here are the only ones with that are on a GitHub. So the other ones are more of a research state, but we're very happy to share. Basically every one of our papers we can share the code for if people want to get their hands on it and play with these things.
Okay, great.
Yeah, thank you. Any other questions? Yeah, I see. Yeah, you can unmute yourself, Juan.
Good morning. Yes, what I would like to ask is whether you have an example of an application of your framework to physical systems driven by stochastic differential equations.
That is a great question, especially for semiconductors, because thermal noise is something that we're very interested in. Once you start talking about stochastic differential equations, there are other kinds of physics compatibility that comes in, right? Not just stuff about conservation and so on, but things related to the second law of thermodynamics and entropy, and in particular, discrete preservation of fluctuation dissipation theorems for these kind of physical systems, right? Where if you have a closed system, whatever random forcing, whatever work you're doing on a system through random forcing, it has to be exactly equal to what's being dissipated out. And so we, I'm hoping, I don't want to talk too much about it, but we have something looking exactly at this that we're submitting to NeurIPS. So hopefully in a month or so, we will have a paper out about that. So please feel free, if that's something that you're interested in, please feel free to send me an email and I will send you the manuscript when we put it out.
Okay, thank you.
Yep.
All right. The next question is Jean Ragusa. Do you want to unmute yourself?
Yeah, that's okay. Thank you. Thanks, Nate, for the talk. I was wondering if you had any recommendation for positivity preserving using neural network, and if the partition of unity approach could help, since often we have the Gibbs phenomena at interfaces, or generally, what are your recommendations for positivity preserving, for example?
So kind of the philosophy that our group uses for everything is to go to the forward simulation world, look at how those discretizations work, and then just like parameterize it, and then you know that you can at least recover the standard theory, right? That kind of all these things that we've done have that feel to it. Right, so the kind of machinery that you can look at a discrete level, right? It's things like an M matrix property. Those are the typical mathematical tools, right? So you want, I'm trying hard not to spill too much of the secret sauce about what my collaborator's been working on, but definitely that's the name of the game, right? Is to figure out how you can design an architecture which can preserve something like that.
Yeah. Typically with the M matrix theory approach, you end up with first order method that are kind of not the type of things you want to do, and in the FEM world, you usually look at the connectivity to derive a higher order viscosity and those type of things.
Yeah, absolutely. So, you know, we're in kind of a unique setting where there is no order of convergence, right? Because we're not trying to get a good answer through mesh refinement, right? We work on a very coarse grid, and then we get a good model by training it to fit a high fidelity set of data, right? So even though traditionally in the forward simulation world, you would avoid a first order scheme, or you know, maybe you wouldn't avoid it, but it would be the first step. In this setting, it's actually perfectly effective, right? There are other things you can do that we've been looking into, like flex corrected transport and things like that. But yeah. I mean, there's all sorts. It's pretty wide open. There hasn't been a lot of work done in this space right now, that I know of, at least.
Okay, thank you.
Right. Other questions? So I had a question about the Maxwell's equation. I was wondering whether there, I mean, you can include information about equivariance with respect to the Lorentz group. I mean, is this something that you are taking into account in your work, or can it be done, I mean, from your point of view?
Yeah, we're just starting to so I kind of mentioned, I kind of alluded to this about stochastic PDEs, right? In terms of compatible treatment of dynamical systems and PDE models, there's kind of two distinct groups. There's spatially compatible PDE models. That's mostly what I presented today. In the dynamical systems world, there's geometric integrators, things like what Jerry Marsden and all of them worked on for a very long time. So my group, and we're starting to focus on the latter, right? So the kind of things that you mentioned, you can actually see a lot of this starting to break through right now. Like at NeurIPS, the last 2 years or so, there's been a explosion of like Hamiltonian networks, symplectic networks, and so on. Those are very limited in terms of they're really restricted to reversible systems and things like that. Yeah, that's a great suggestion. It's along the lines of the kind of stuff we're looking at right now.
Yeah, all right, thank you. Yeah, I'll send you an email anyway. I think it's very interesting. Yeah, work. Yeah, thank you. Any other questions? Yeah, all right. Thanks a lot, Nat, for the very good talk. Thanks a lot, and I'll just on behalf of everyone else.
Well, thank you very much for having me.
Yeah, thank you. Take care, everyone. Thanks. Bye.
Bye.